Hello my friends and welcome back to the Today Machine channel. The manufacturing of cylinder crankcases for large engines is a highly specialized process, driven by the need for precision, durability, and performance. Guinanth, a global leader in this field, focuses on delivering state-of-the-art solutions for various industries. The process starts with casting, where molten iron or aluminum is poured into custom-designed molds. These molds are engineered to produce complex, optimized geometries that improve the power-to-weight ratio of the crankcase, ultimately enhancing engine efficiency. Once casting is complete, the crankcase is cooled and solidified. It then undergoes rough machining to remove excess material and prepare it for more refined operations. CNC machining is employed to achieve the tight tolerances required for large engine components. Following machining, the crankcase is subjected to heat treatments, such as annealing, to relieve internal stresses and improve its mechanical properties. The production process also includes drilling, honing, and threading to accommodate engine components and ensure a perfect fit. Throughout the manufacturing stages, rigorous quality control measures, such as ultrasonic and X-ray inspections, are implemented to detect and correct any internal defects. In the final steps, surface treatments like coatings are applied to enhance corrosion resistance and longevity. Cylinder crankcases produced by Guinanth are also designed to support engines using alternative fuels, such as hydrogen, contributing to a more sustainable future. This combination of advanced manufacturing processes and stringent quality standards ensures the production of high-performance crankcases that meet the evolving needs of the modern world. The production of cast iron components has undergone significant advancements, driven by the increasing demands of modern industries. The process begins with the melting of iron in energy-optimized furnaces, where raw materials like scrap iron are combined with alloying elements such as carbon and silicon. This molten iron is then poured into sand or other refractory molds, which are specifically designed to shape the final product. Advanced molding techniques, including automated and 3D printed molds, are used to ensure precision and efficiency. Once the molten iron cools and solidifies, the casting is removed from the mold and excess material is trimmed away during the fettling process. To enhance the strength and ductility of the cast iron, heat treatments such as annealing or tempering are applied. Machining is a critical phase in the manufacturing process, where components are shaped to meet specific tolerances. CNC machining ensures that every part is produced to exact dimensions. Drilling, grinding, and polishing processes are often performed, depending on the complexity of the component. Quality control is a key element of cast iron manufacturing at Guinanth. The use of material testing methods, such as hardness testing and ultrasonic inspection, guarantees that each component meets the required specifications. Additional surface treatments like priming or painting provide corrosion resistance, making the components suitable for use in harsh environments. These cast iron solutions are not only essential for today's mobility and energy sectors but also contribute to the development of sustainable, future-ready infrastructure. Guinanth's long-standing expertise in metallurgy, combined with state-of-the-art manufacturing technologies, enables the production of highly reliable cast iron components. These components are critical for industries as diverse as transportation, agriculture, and energy, ensuring efficiency and sustainability in the global market. The manufacturing of a wind turbine hub, weighing approximately 35,000 kilograms, involves a highly specialized casting process. Utilizing mechanized molding systems and manual casting techniques, the process employs hand-molded cores produced using height-adjustable continuous mixers. The molds and cores are created with the fur and resin molding process, ensuring dimensional accuracy and superior surface quality for large castings, which can weigh up to 65 tons. Muselwitz Gus offers comprehensive design support, replacing welded constructions with cast solutions, and advising on material selection and casting-friendly design. Their in-house model-making capabilities enable the production of precise models quickly, facilitating rapid adjustments and refurbishments. In the Foundry, 3 medium-frequency induction furnaces with capacities of 12 tons each, and 1 furnace with a capacity of 36 tons, ensure reliable melting. The process is monitored by a 24-element spectrometer and supported by an automated charging system, ensuring high-quality molten material for each casting. The mechanical processing and coating of these cast components are handled by expert partners. This includes treatments like galvanizing, thermal spraying, priming, and painting, with documentation provided as requested. From the early design phase, technicians use advanced tools like solidification simulation, mold filling simulation, and deformation prediction during cooling. These technologies help improve the quality, reliability, and cost-effectiveness of the castings while reducing development time. Manufacturing injection and compression molds involves a complex and precise process designed to create durable, high-performance molds for various industries. The process begins with design and engineering, where mold makers collaborate with clients to develop molds that meet specific requirements for size, material, and performance. Advanced CAD/CAM software is often used to create detailed 3D models of the mold, ensuring accuracy before production begins. For injection molds, the focus is on creating molds capable of shaping thermoplastic materials under high pressure. These molds typically feature multiple cavities, allowing for high-volume production of identical parts. Precision machining, such as CNC milling and EDM, electrical discharge machining, is used to shape the mold components, which are then assembled and polished for smooth operation. In contrast, compression molds are used for molding thermoset materials and carbon fibers. These molds are designed to withstand high pressure and temperature, ensuring the proper curing of materials. The manufacturing process includes similar precision machining but with specific considerations for thermal management and material flow. In hand-molded casting for a crankcase, the mold assembly process is essential to ensure a precise and durable casting. At Muselwitz Gus, the mold pieces are carefully prepared and assembled in the casting pit. The process starts by positioning the pre-manufactured mold sections, including both the cope, upper part, and the drag, lower part, in a pre-dug pit. The mold is typically composed of sand reinforced by binders to provide the necessary rigidity and detailed contours. For crankcases, the mold is designed with multiple sections to capture complex geometries, including internal passages and mounting points. Once the individual mold sections are in place, they are precisely aligned using alignment pins or guide systems. This ensures a tight fit between the mold halves, reducing the chances of casting defects such as flash or mismatch. Core placement is another crucial aspect of mold assembly. Cores, often made from hardened sand, form the internal cavities of the crankcase, such as the areas for oil channels and bearing surfaces. These are positioned inside the mold according to the design specifications. After the mold assembly is complete, heavy plates are inserted on top of the mold structure. This plate helps compress the mold, ensuring that it retains its shape during the high-pressure casting process and preventing any shift or distortion when the molten iron is poured. The molten iron, prepared in a furnace, is heated to the appropriate casting temperature, which typically ranges between 1200 degrees Celsius and 1400 degrees Celsius, depending on the material specifications. Once the iron is ready, it is carefully poured into the mold through designated gating systems. These gates and risers are designed to channel the molten metal smoothly, filling the entire cavity while avoiding turbulence, which could introduce defects. After filling, the mold is left to cool, allowing the molten iron to solidify into the desired crankcase shape. The process of pouring molten metal into cast iron molds is a critical step in metal casting, typically used to create complex metal components. In this process, molten metal is poured into a mold cavity formed in cast iron, allowing it to cool and solidify into the desired shape. This method is particularly popular due to cast iron's excellent heat retention and resistance to deformation during the cooling process. Before pouring molten metal, the cast iron mold is carefully prepared. The cavity inside the mold is designed to match the dimensions of the final product, with allowances for shrinkage as the metal cools. For example, the shrinkage rate for metals like steel is around 2%, while aluminum shrinks about 1.3%. The mold also includes risers and runners to allow for proper flow of metal and gas escape. In many foundries, the molten metal is produced using an induction furnace or a cupola furnace. For instance, a 3-ton induction furnace can melt steel at temperatures ranging from 1400 degrees Celsius to 1600 degrees Celsius, depending on the alloy. The melting process can take 1 to 2 hours, depending on the batch size and type of metal. Once the metal reaches the desired temperature, it is carefully transported to the cast iron molds, typically using a ladle. The ladle must have sufficient capacity, such as a 500 kilograms or 1000 kilograms capacity, depending on the casting size. The pouring temperature is crucial. For cast iron, it ranges between 1150 degrees Celsius and 1250 degrees Celsius. A controlled pouring rate ensures the mold is filled evenly, minimizing turbulence that could lead to defects like air pockets or inclusions. This can take anywhere from 30 seconds to a few minutes for larger castings. After the mold is filled, the metal begins to solidify. Cooling rates vary depending on the type of metal and mold thickness, but generally, it can take between 30 minutes to several hours for the metal to fully solidify. A thicker mold may require more time to cool, while thinner molds cool faster. For large castings, cooling times can extend up to 24 hours to avoid internal stresses or cracking. Once the metal has solidified and cooled sufficiently, the mold is broken apart to release the casting. Any excess metal from risers or runners is removed, and the casting undergoes finishing processes such as grinding or heat treatment to achieve the final specifications. This moving column milling machine operates by shifting the milling head along a fixed bed while the workpiece remains stationary. This design allows the machine to handle large parts with varying shapes and dimensions, making it highly versatile. The machine's main movement is guided on a robust bed reinforced with internal ribs, ensuring system rigidity. The milling process takes place with the column assembly, which moves in three axes, X, Y, and Z. The X-axis carriage moves the column along the bed, guided by two linear tracks, supported by sliders with roller recirculation. The double rack and pinion system powers the X-axis, providing stability and precision when machining long parts. One of the key advantages of the moving column design is its ability to machine parts independent of their location and fixings. This flexibility enables the machine to accommodate a wide range of part sizes and shapes, whether large or heavy. The high accuracy and repeatability of movements, combined with guide tracks, ensure precise machining. For operator comfort and control, the machine is designed with an accessible cab, either fixed or with vertical movement, and dual control panels for easy operation from both the cab and the machine's front. This setup allows for efficient monitoring and adjustments during the machining process. The Lagan bed mill is a robust, modular milling machine with an integrated rotary table, designed for flexibility and precision. Its rotary table offers high load capacity, enabling the machining of long or complex workpieces. With interchangeable components like slides, rams, and columns, the machine enhances rigidity and ergonomic comfort for operators. It has a longitudinal X-travel of 3, 4, or 5 meters, making it ideal for large-scale or 5-sided milling. The machine's optimized working area and internal space allow for machining various shapes and sizes, while efficient swarf and coolant removal ensures smooth operation. The video is set entirely in a foundry and vividly illustrates the process that transforms a model into a finished cast iron product. Early in the morning, the furnaces are already operating, preparing for the day's work. In the molding department, a model of an imposing base, made by Neri, is ready for casting. The model consists of two parts. First, a release agent is applied to the model, which helps to prevent sticking during the molding process. The model is then placed inside a large steel flask. The flask is filled with a special sand resin mixture, which hardens and takes on the exact shape of the model. To identify the flask, the operators imprint the name of the customer into the sand. It takes about 10 minutes for the sand to harden. Once the sand has solidified and the mold has taken shape, the flask containing the impression left by the model is lifted. Certain parts of the model are carefully removed by hand to avoid damaging the mold. After this, the mold is treated with an iron oxide coating, which enhances the surface quality of the cast iron. This coating is then dried in an oven to prepare it for the next stages. The two halves of the mold are placed side by side. In the lower half, a core is inserted. This core is smaller than the final product by about a centimeter and determines the thickness of the cast iron at the end of the pouring process. Placing the core is a delicate operation, requiring precision to ensure the correct final product dimensions. Next, the second half of the mold is rotated 180 degrees and placed on top of the first half. Alignment pins guide the two halves into position, ensuring they are properly aligned. These pins play a crucial role in guaranteeing the accuracy of the final casting. The cast iron is melted in an 18-ton oxy-combustion rotary furnace. It takes 2 hours to reach a temperature of 1,500 degrees Celsius, which is necessary to melt the metal. Once the metal has fully melted, it is poured into a ladle. Any slag floating on the surface of the molten metal is skimmed off, and a probe measures the temperature to ensure the cast iron is at the correct heat. The molten metal is then poured into each of the prepared molds, filling them one by one. The following day, a large mechanical arm removes the casting from the flask, breaking it free from the surrounding sand. The cleaning process takes place inside a shot blaster, where small steel balls are fired at the surface of the casting for a few minutes, effectively removing any remaining sand and debris. When the casting emerges from the shot blaster, its surface is perfectly clean, though there are still burrs to remove. The piece is now ready for any further finishing operations, which will be completed at Neri. Steel billets are semi-finished products that serve as the starting material for many manufacturing processes, including forging. These billets are often rectangular or round bars made of steel. Before the billets can be forged, they need to be cut to the desired length. High-speed saws are used to cut the billet into smaller, more manageable pieces. The length of the pieces is usually determined by the dimensions of the final product. After cutting, the steel billets are heated to a high temperature, typically between 1,100 and 1,300 degrees Celsius, depending on the type of steel and the specific forging operation. Heating softens the material and prepares it for deformation. The heat also improves the steel's ductility, making it easier to manipulate during the forging process. Upset forging is the process where the billet is compressed in the axial direction, increasing its diameter while reducing its length. This process is commonly used for parts that need to have a larger cross-section at one end, such as bolts and fasteners. Upsetting requires precise control of temperature and pressure to ensure that the material flows properly and does not crack. The key is to achieve the desired shape while maintaining the integrity of the steel. In the setting down phase, the material is hammered or pressed into a more defined shape after initial upsetting. This process further refines the geometry of the part by squaring off edges or compressing specific areas to achieve the desired thickness or width. Setting down ensures that the material density is uniform throughout the part, which is crucial for components that will undergo heavy loads or stress during use. Solid forging involves shaping the billet without creating any hollow sections. It is typically performed using dies and hammers to compress the material into a solid form. This technique is suitable for parts that require high strength and density, such as crankshafts, connecting rods, and gears. Cogging is a form of forging used to reduce the cross-sectional area of a billet in a controlled manner. This is done through a series of blows or presses, where the material is gradually elongated and thinned. The cogging process also helps to break down the grain structure of the steel, improving its mechanical properties. Scarfing. Surface imperfections such as scales, seams, and impurities are removed from the steel billet. This is done by heating and then scraping off the surface material. Removing these impurities is crucial as they can weaken the forged part and lead to defects during use. In some forging processes, coal is added as a lubricant to facilitate the flow of the material and reduce friction between the billet and the dies. Turning around is a process used to ensure that the billet is evenly heated and forged from all sides. During forging, the billet is often rotated or turned to make sure that the pressure is applied uniformly. Hollow forging is a method used to create hollow parts, such as tubes or hollow shafts, by forging the steel around a mandrel or core. The material is shaped around a core to create the desired internal geometry while maintaining structural integrity. In manufacturing, the straw boss is a term used for a supervisor or foreman who oversees the forging process. Their role includes ensuring that all operations are carried out efficiently, maintaining the quality of the product, and making quick decisions to avoid production delays. Tap forging is used to create threads on a forged part, often required for bolts, screws, or any part that needs a threaded section for fastening. The material is shaped and compressed in such a way that the threads are formed directly during forging rather than being machined afterward. After forging, some parts may not have perfect geometries due to the stresses involved during the process. Forging cut is the final cutting stage of the forging process, where excess material is trimmed off the forged part to meet the exact dimensions. This is usually done using shears or cutting presses designed to handle forged materials. After the forging is complete, the parts are cut to their final dimensions and marked. The marking process involves stamping the part with a unique identifier, such as a batch number or serial number, to track its production history. Once the forging process is complete, the steel components undergo several additional procedures to enhance their mechanical properties and prepare them for final applications. Heat treatment, machining, and inspection ensure that the forged parts are durable, precise, and free from defects. Heat treatment is a crucial step in manufacturing as it alters the mechanical properties of the steel to improve hardness, toughness, and strength. The heat treatment process typically involves three main steps: normalizing, tempering, and quenching. In tempering, the steel is reheated to a lower temperature and held for a specific time before cooling. Quenching involves rapidly cooling the heated steel by immersing it in water, oil, or other quenching mediums. This process increases the hardness and strength of the steel but can also make it brittle. Normalizing is the process of heating the forged steel to a specific temperature and then allowing it to cool in air. This process refines the grain structure, relieves internal stresses, and ensures uniformity throughout the material. Normalizing is essential for components that will be subjected to further machining or high-stress applications. Tempering, as described, is applied after quenching to balance hardness and toughness. After heat treatment, machining is performed to achieve the final shape and dimensions of the part. Machining processes are highly precise and often performed using advanced equipment like CNC machines. A machining center equipped with a Mazitrol smart control system is often used for precise operations. This system allows operators to program complex machining cycles for turning, milling, and drilling. Five-phases machining is particularly useful for large or complex parts, enabling multiple surfaces to be machined in a single setup, which reduces the need for repositioning and enhances precision. Lathe machining is another important operation, especially for cylindrical parts such as shafts or rods. The lathe spins the part while a cutting tool shapes it, ensuring uniformity and precision. Dimension measurement is conducted using precision instruments like calipers, micrometers, and coordinate measuring machines, CMMs, to ensure the part adheres to required specifications. Non-destructive testing methods such as magnetic particle testing and ultrasonic testing are used to detect internal or surface defects that might not be visible to the naked eye. Magnetic particle testing is useful for identifying surface cracks, while ultrasonic testing can detect internal flaws by sending high-frequency sound waves through the part.